Okay, good morning. This morning we have a low attendance. There's a strike in Rome of transportation, so thanks for being here. We will complete today all aspects concerning trajectory planning. As I mentioned last time, we start with this decomposition: joint space trajectory planning and Cartesian space trajectory planning, but many of the techniques actually can be moved from one space to the other, and this will be clear from the context. We mentioned that the other basic concept is this separation of geometric aspect of the trajectory, which is the path that the end effector or the joints should trace, and the timing law associated to this motion. Okay? And now we will see some examples. So we started, this is before last slide of last time, we started with trajectory planning in the joint space, where we specify a class of trajectories, and we don't make much distinction at this stage between time and parameter. So what I write in time could be written in parameter and vice versa, saving the fact that I can speak of velocity and acceleration when I take time derivative of quantities. I should speak of path tangent, path curvature when I take the derivative with respect to the arc parameter. Okay? Otherwise, everything is very similar. So we choose a class of function for interpolating, and we impose condition on the parameter of this class of function. If the class of function, as we will see, is often a polynomial, we will impose condition on the coefficient so that we can determine in a unique way our polynomial. Okay? These coefficients, these conditions include passage through points. And if we design a point-to-point trajectory where there's only one initial point and a final point, then these are really the boundary geometric condition of our motion. We may specify initial and final velocity or intermediate velocity if we have internal knots, acceleration, and by choosing the class of function, we impose automatically also the continuity. Okay? If we use polynomial function, a polynomial is C infinite. We can take derivative no matter how many. Okay? Of course, if it's a finite order polynomial, after some derivative, it will be identically 0. Okay? So this is not a major issue. Again, I spoke in the black terms, so in terms of time, but here in green you will find also the equivalent concept when we are parameterizing things with respect to a parameter lambda. So this was the first example, and we introduced the interesting notion of doubly normalized polynomial. So this is a cubic polynomial, which is written in this particular form. So instead of writing a generic polynomial like this one, let's say q of t, and I'm using different notation, a t of dt square plus ct plus d, which is a generic third order polynomial with 4 coefficients. Okay? I've used this format, which essentially reorganizes the structure so that we put in evidence a doubly normalized polynomial. By this I mean a polynomial which is normalized in time, so we use tau rather than t, with tau going from 0 to 1, while the original time t goes from 0 to capital T, which is the total motion time desired. And then we factor out the variation. So we are working for a generic joint. Remember, now it's all scalar notation because you can do this joint by joint. So the delta q is the variation. It may be positive or negative. You add the initial value, and now you have condition on the doubly normalized polynomial qn of tau, which should go from tau 0 to tau 1 and move from 0 to 1, because when it's 1, it multiplies delta q and it gives the final configuration q final. Okay? So this is the idea. And then you can impose the condition and solve for this, and you find a very nice structure with only two coefficients which are different from 0. They are integer, sum up to 1, and they have opposite sign. We will find this later. It's a general property when you're working with double normalized polynomial and you're imposing 0 boundary condition on velocity or higher order derivative. So a rest-to-rest motion. So now let's move to the next example. Again, I'm starting just to show, I'm starting from something in between. So I'm using now a quintic polynomial, normalizing only with respect to time, not normalizing on space. This quintic polynomial has 6 coefficients. It means that we can impose up to 6 conditions. For instance, we can impose the fact that on this normalized in time polynomial, we start at t0 in q0, at t equal capital T or equivalent T, tau equal 1, we should be in q1, so the final point. And then we have some initial velocity v0 and final velocity v1 and acceleration a0 and final acceleration a1. When we write this in terms of the normalized time, remember, you have to add for the first derivative a factor t, for the second derivative a factor t squared, and I guess you can imagine for the kth derivative a factor t to the kth power, okay? Just because of the relation between tau and t. So when you impose this for general boundary conditions, so this is not a rest-to-rest motion. You can start with non-zero velocity and reach the final point with 0 velocity or vice versa, or both velocity are different from 0. The acceleration may be 0 or not, one or the other or both, and so on. So here you find a solution already written in this special form. This is if you have happened to find this in some numerical analysis course. This is a form which is also called Lagrange or Lagrange-like form of polynomial. In fact, if I should write it in general, and I'm saying I want to define a quintic polynomial, so of degree 5, and I want to interpolate condition at some initial point and some final point only. Then I would write this as q tau, and this is the general form, 1 minus tau q, and then, let's see, I don't want to use the same condition, let's say a plus b tau plus c tau square, and then plus some symmetric term, which is c plus d 1 minus tau plus a, b, c, d, oh, sorry, d, and then f 1 minus tau square. So you recognize this? So this is the general format. It's another way of writing a polynomial of degree 5, like the one on top. But it has a nice structure. Why? Because thanks to this factorization, those coefficients will depend only on the condition imposed in tau 0. Position, velocity, acceleration. While this coefficient will only depend on the condition imposed on tau 1. And in fact, you see only zeros here and only 1 here. So it's a very robust way in order to do computation by hand, but also for evaluating this numerically. Okay? You can, of course, reorganize things and find the A, B, C, D, F coefficient, small coefficient of the first line from here. No problem. Now again, look at this. If you impose a rest-to-rest motion, so you start with zero velocity and end with zero velocity and also with zero acceleration and zero initial and final acceleration. Okay, so you put zeros to this. Then you can reorganize things exactly in this double normalized form where you start from Q0, delta Q is the variation Q1 minus Q0, and here you have the doubly normalized polynomial with tau going from 0 to 1 and in time, let's say, and with this polynomial moving from 0 to 1 at the end point. And again you find 6 minus 15, 10. So only half of the coefficients are different from 0. You see there's no terms in tau square, in tau, or the constant term. So the higher, only the half of the coefficient of higher order terms are different from 0. They are integers, no matter what time you want to impose for this motion. For instance, 1.322 second. This is completely transparent. It's inside tau, because tau is T over capital T. Okay? And no matter which is the variation, because this is internal here. So these coefficients are computed once forever. I insist on this because I find many textbooks are using strange number when they provide examples. I don't have to provide examples because this number apply to any variation in time and duration. Also, they sum up to 1. You see it? And they have opposite sign. This is a general property, as I mentioned. Okay? So let me do a small table which recaps these things, or maybe it's not yet the time. Okay. We will come back on this later on. First, we do something else. So I'm providing examples. No? The first two examples were point-to-point motion, only first point, last point. Now, in the joint space, but if you wish, also in the Cartesian space, there's another interesting, very practical case, which is connected to one of the typical tasks of the robot, meaning picking something in a place and placing it somewhere else. Okay, so the pick and place operation. Now this pick and place operation typically involves some support, some table, or some conveyor belt. So the robot should start and very carefully move out because it's in contact with the object, with the environment. So it should start from that place and detach or depart. Then it can make the large motion, and then when approaching should have another via point before getting to the final point where probably the object that it is hold will be in touch with the environment. Okay? So this total motion, and if you think of this pick and place operation, you can understand also the terminology, has three phases: a lift-off phase, a travel phase, and a set-down phase. Okay? Why are we adding these two intermediate points? You can imagine it very clearly in the Cartesian space, although this planning is made in the joint space. You see that things gets mixed sometimes. So these 2 points are imposed so that the initial and final part of this trajectory do not have any wandering of overshooting. So that we really are very carefully departing from a touch condition, do whatever we do, and then approaching and touching again the environment. Okay? So this is the rationale. So how do we set this problem? Well, first of all, initial point, depart point, approach point, and final point, if they were coming from the Cartesian space, they are inverted in the joint space with kinematic inversion. And now for each joint, we have some value. And so, again, this graph concerns a generic joint, which should go from Q0 at some, now I'm planning in time, at some time T0, typically 0. It should go through Q1 at time T1, go through Q2 at time T2, and then reach the final point QF at time TF. Okay. Now, I could use a single function going through. But I want to, I mean, in order to impose all conditions, I would need a higher order polynomial. And higher order polynomial interpolating things are no good. We will comment on this later. So this is why this is a first example of patching together low order polynomials. So the other condition that I want to impose is I want to start very softly, so 0 initial velocity or some, 0 initial velocity and 0 initial acceleration. And these are, sorry, this and this condition. Similarly, at the final point, 0 final velocity, 0 final acceleration. Now there are other conditions that I'm imposing. So passage through 4 points, and then 2 conditions on derivative at the initial point and 2 conditions at the final point. Since I'm not using a single polynomial, but I will patch 3 polynomials in this case, I should guarantee that there is some continuity in the intermediate point. Because if I'm using only one polynomial, this is automatically continuous. Okay? It's the fact that I'm using multiple polynomials and joining them at the knots that requires to impose some additional condition, which is, okay, so this is just the passage. So the polynomial on the left and the polynomial on the right of this point should both interpolate Q1. If I had only one polynomial, this would be passing through Q1, so it would be only one condition. Now there's 2 conditions, because both should be interpolated from the right and left. Same for the point Q2. In addition, I would like to preserve some continuity also for higher order derivative. Velocity should be the same, left and right, and acceleration should be the same, left and right, on the 2 intermediate knots. Okay? So if I count all conditions that I would like to impose, I have 6 passages. Why 6? Because the 4 initial and then this duplication. Okay? Plus 4 given condition on the initial and final acceleration, plus 4 continuity condition up to the acceleration. Okay? So a total of 14 conditions. So I could work it out with a polynomial of degree what? In order to have enough degrees of freedom to satisfy 14 conditions. The polynomial should be of what degree? 13, because it has 14 coefficients. But then it would be crazy, because those continuity conditions would be automatically satisfied if I'm using only one polynomial. So, okay, so probably I need less. But I don't do this. I'm using a combination which is called 4-3-4. So a polynomial of degree 4 in the first phase, 3, so a cubic in the second, and 4 at the end. So this Q lift, Q travel, and Q set down polynomials will have a total of 14 coefficients, which is what I need. Pay attention. It's also a good choice. It's symmetric, so that the coefficients are well distributed over boundary condition. Because if I'm using, let's see, a first order polynomial here, 2 coefficients. First order polynomial here, other 2 coefficients, and we are 4. And then a 9th order polynomial here, the total number of coefficients would be again 14. But there's something wrong here, because my coefficients are not where I need it for imposing the condition. So I need to distribute this in a, let's say intelligence would be too much. I mean, in a non-stupid way, I would say. And this is why you have this type of form. It's not the unique patching of low-order polynomial, but it's the lowest order that guarantees the result. Okay? Now, I don't give you the coefficient. You can find it in the literature or in the internet. They are pretty much involved, but this is something that you can write a MATLAB code and do, and have it ready for any particular data. And you can use all the tricks of using normalized polynomial, restarting from 0 when you're here and here, so that the solution is almost in closed form. Does not require otherwise, in general, the solution of a set of linear equation in the unknown coefficient. So, higher order polynomial. And now it's time for making this table. So suppose that, again, we go back to the previous case of point-to-point motion. So we have only one initial configuration and final configuration to be interpolated. And we want to be very smooth at the beginning and at the end, meaning that we want to impose 0 velocities, 0 acceleration, 0 jerk, and so on and so on. Okay? Now we can solve this by using this doubly normalized polynomial. In fact, we have already seen 2 examples, and I'm writing them again on the blackboard. So let's put here n, the degree of the polynomial, and we have already worked with a degree 3 and 5. Let's put now also a 7, then it will be a 9, and so on. Okay, so you see that, first of all, we are considering only interpolating polynomial of odd degree, not of even degree. Why? Because they have an even number of coefficients, which are divided in 2 to impose condition at the start and at the end. This makes sense. Then they are doubly normalized, and in fact this Qn of tau, for this case, I write it again, I have a table, it's minus 2 tau to the third plus 3 t squared. So this was the first example, the cubic rest to rest, when you're going to 0 velocity and 0 initial velocity and 0 final velocity. Okay? By the way, you can also compute Qn prime of t, which is dQn with respect d tau, so the derivative with respect to this normalized time, not the original time. And here you see that this is minus 6t squared plus 6t, or if you wish, 6 tau times 1 minus tau. Okay, and then you can compute also the second derivative, and so on. So in a pretty much easy form. And then you can evaluate, for instance, the maximum first derivative of this and the maximum second derivative, where it is and what is its value. Okay? What is missing is time, but then if you want to write q dot n of tau, which means derivative of Qn of tau with respect to time, time, not tau, well, this is Qn prime of tau, and then you take the derivative of, let's write it here, tau is t over t, so this gives a factor 1 over t. Okay? So from here, for instance, just multiply by a 1 over t and you have the velocity, the actual velocity, not the normalized one. Okay? So more in general, if you have a derivative of order k of Qn of tau with respect to tau k times, this is equal to the derivative of Qn of tau with respect to time k times, and then factor 1 over t to the power k. Okay? So you can use this formula very, very neatly. So suppose that you want to impose now also zero initial velocity and zero initial acceleration and zero final acceleration. So with a cubic function, you no longer be able to do this. You need to move up to add two coefficients. So you move from degree 3 to degree 5, and you have 6 coefficients for imposing initial position and final position, and zero initial velocity and acceleration, and zero final velocity and acceleration. Okay, and the resulting polynomial, we have written it before, but now I'm writing it again, is starting 6 tau cube minus 15 tau square plus 10 tau to the third. Exactly what we found before. Of course, I'm assuming that I have to move a delta q equal to 1. If not, I multiply by the delta q. Okay, so I'm just referring to the doubly normalized polynomial. We can compute also the first derivative, and this is, let's see, 30 tau to the fourth. In fact, I can also take it. Then minus 60 tau to the 3. So I take out the 30, so I have a minus 2 tau to the third. And here again, plus 30 tau to the second. 30 is outside, so plus tau to the second. And then I can compute also the second derivative and so on. You see that after some derivation, this goes to 0. All goes to 0, of course. Okay? And now, if you need to impose also initial and final jerk, same story. You take a polynomial of degree 7, you write it in this normalized, doubly normalized form, you impose things, you solve it, you can do it numerically, but if you do this for higher order polynomials, you will have some rounding of error when you're solving your system of linear equation, but you know that you can eliminate all roundings because there is this rule that is stated also in the slide. And in fact, for degree 7, you have minus 20 tau to the 7 plus 70 tau to the 6 minus 84 tau to the 5 plus 35 tau to the fourth. Okay, and the first derivative is just 140 in evidence minus tau to the sixth plus 3 tau to the fifth minus 3 tau to the fourth plus t. Okay, and so on and so on. So this is a very nice property, no? Because really try to build a MATLAB program doing this for any generic order. Of course, you should always take odd order of polynomial, and you will find that when you reach 9 equal to, let's say, 15, you don't get such nice number. You may get, for instance, here 84.01. This is just numerical approximation. Okay, so you can get rid of that. In fact, you could try to solve symbolically this set of equations, and then you will find the exact number in infinite precision, because you know that you have this. So this is very nice. So, very good, and we will see that through example, a couple of examples, that this polynomial, outside the interpolating initial and final point, do not wander at all. So they are all contained between the initial and final value. And this is a very nice property. Okay, they are very smooth, don't wander. So everything works, but pay attention. We can go up to the degree whatever, 25, 27, but use them only in this situation. When you're using this for interpolating multiple knots, then this is the worst choice that you can do, because you, at that time, since you are not constraining at the initial and final point all derivatives to 0, you will have maximum and minimum distributed over the whole path, and so the high order polynomial will oscillate and wander outside the interpolating knot. So it's not the use that you should make it. So let's make two examples of this class of trajectory. So this is the 9th degree polynomial, the one that I have not written here, but I have a MATLAB program doing this, and then do the plot. So you see doubly normalized, so between 0 and 1 is tau. I don't care if then I will be asked to do this motion in 2.5 seconds. I will just multiply things. And going from 0 to 1, whatever is the joint increment that this generic joint should make. And you see that it starts very softly. It seems to be 0. It's not 0. Remember that these are smooth functions. If an analytic function, this is calculus 1, if an analytic function is 0 or constant over a finite time interval, then it's 0 everywhere or constant everywhere. So this is 0 only in one point, but since the higher order derivative are 0, it starts very softly, then does the motion, and then reaches very softly in a symmetric way. Okay? In fact, this is the first order derivative. Okay? The normalized velocity is not the velocity or speed, whatever. Okay, so from 0 to 1, and here the peak, which is computed essentially taking the derivative, the maximum is at tau equals 0.5, so at the midpoint, and the value is obtained by setting this there. Okay. Now, if you impose even more boundary condition, for instance, here, this is a 29th degree of the same kind, polynomial, so with 30 coefficients. Only the higher order 15, the half of them, are different from 0. They are integers, alternating sign, summing up to 1, and they provide no overshooting or wandering. So it's very slow start, then does the motion and almost flat arrival. Okay? Such kind of polynomials are used, for instance, when planning trajectory for flexible manipulator arms. When you have flexible links, since if you give a step input to those systems, they will start to excite all vibration modes. So they will start to vibrate wildly. So you try to start very smoothly and reach the end very smoothly. And this is not guaranteeing anything, but in practice it's very convenient to not excite higher order frequencies of vibration. Okay? So this is why this is of interest. Okay? So here I'm imposing 29. I already know that I will impose the first 14 derivatives to 0 here and there. Okay? 30 coefficient, 15 used for imposing here and 15 there. One is using for imposing the passes through 0, the other 14 for imposing 0th derivative up to the order 14. Okay, and same at the end. But look at the normalized velocity. It's exactly the same motion, same normalized time, same increment normalized to 1, but here you have a peak which is 4.5, here you had 2.5, so almost doubled. Why is that? Because since you're imposing no motion practically for some larger interval or very small motion, so the largest variation is concentrated in less time, so there will be a peak. So this is the counter effect of such approach. Okay, so good and bad, but it's good to have this in your portfolio of planning tools. So we mentioned that this should not be used for interpolating multiple points. So what to do then? There are several ways for doing interpolation, and one classical is using splines. Actually, splines are a whole large class of function, of interpolating function, we will use conventional splines, not B-spline or X-spline. There are books on this. Doing exactly the interpolation. These have been used also for the design of car bodies. There's an algorithm, famous algorithm given by Castelgeot, who was a designer at Citroën in the 1950, who designed the surface of their car body using this type of splines or variation of this. So they are really intended to interpolate many points and interpolated with some smoothness constraint, avoiding overshooting, undershooting, so that you get a nice, smooth, natural path. The term spline in English denotes an object which can be deformed and are used by drawers to make interpolation by hand. So it's like plastic things that can be arranged. And being a material, there is some continuity. There's no discontinuity when you try to bend this material. Okay? So why splines are used? And then we'll see how they... Suppose that you have to interpolate many points. So these are n very large. And this is the generic time or lambda. And this is the generic joint Q. Okay. So suppose that n is, let's say, 1, 2, 3, 4, 5, 6, 7, 8. It's already a good number. So if I don't want to impose other condition, or if I want to impose, let's say, start 0 velocity and final 0 velocity, so n is equal to 8, plus the 2 initial condition, 10 condition, I need a 9th order polynomial. Okay? So a 9th order polynomial, its first derivative will be an 8th order polynomial. How many roots has the first derivative equal to 0 equation? Since it's a polynomial of degree 8, it has 8 roots. So there are 8 points where the polynomial has a maximum or a minimum. Okay? Now, where are these placed? They could be placed outside the interval of interest, but typically they could be sorry, this is wrong. So here I have a maximum, 2, 3, 4, 5, 6. There are 2 more probably outside. Okay? Which means that it's true that you're interpolating, but you're going what it's called overshooting. Another interpolation, a better interpolation would be something that does like this. You see the difference. But you cannot guarantee to go there if you're using only a high order polynomial, a single one. And this motivates the use of patching things, exactly like in the 434 case. Now we are generalizing it to a generic number of nodes, n, that can be even very large. And we have seen why it could be very large, because remember this transformation. You get some few points in the Cartesian space from the task planner. They are interpolated, then oversampled, and then all these points moved to the joint space, and then you have to do the interpolation. And this is exactly the case where those results apply. So our problem is interpolate a generic number, typically large, of n knots, and we would like to impose some continuity. Since we are patching together elementary function, which will be cubic polynomial in our cases, all cubic polynomial, so we have to guarantee continuity, and we guarantee continuity up to the second derivative. Now I can say acceleration if this is done in time, or curvature if this is done in space. Okay, it's exactly the same. So what is a spline? A cubic spline in this case. It's a function made by, in this case, n minus 1 cubic polynomial, because there are n knots. so n minus 1 intervals. So I have n minus 1 cubic polynomials that interpolate the knots and give continuity in the intermediate knots. How many intermediate knots are there? Well, here n is equal 8, so the intermediate knots are 6, so n minus 2 in general. Okay? And there you have to impose the matching of first and second derivative. Okay? So this is the continuity. So how many coefficients do we have in total? Well, cubic function have 4 coefficients. There are n minus 1 cubic functions, so 4 times n minus 1 coefficients are there. How many conditions? Now, pay attention how you compute this. You can reason in different way, but here is one. So you can look at the generic cubic function and say, okay, this cubic function should interpolate its, from your side, left knot, yeah, and right knot. Okay, so there are 2 conditions. So 2 conditions for n minus 1 polynomials, cubic polynomials, so passage through all the points imply this number of conditions. Then n minus 2 is continuity in velocity at the intermediate knot, and n minus 2 continuity in acceleration. Okay? Another way of saying would be, okay, I have to interpolate n points, so these are n conditions, and then I have to impose also a continuity of position of which internally, so there are n minus 2, so I have is n plus n minus 2, so it's 2n minus 2 or 2n minus 1, so you reach the same condition. Okay? Depending on how you see things, but so if you add up this, you have 2n plus n plus n, so 4n minus 2 minus 2 minus 2, so minus 6. So it's 4 times n minus 1 minus 2. So it's the same number of this, but 2 are missing. So you can impose 2 other conditions. And now you have several choices. The classical choice is to impose initial velocity and final velocity. So you have squared your system. Okay? But this is not the only possibility. Okay? Another situation would be, which is also very common, would be the fact that out of these n knots, the first and the last one are the same, which would mean that you're doing a cyclic task. Okay, so you're starting in the Cartesian space from here, then you go there, 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 whatever, and then you end up in the same point. Then you map this into the joint space, and you have Q1 is equal to Qn. Now, this does not require an additional condition, because I'm interpolating whatever Q1 and Qn is. If they are the same, okay, this is a special case, but I don't need to impose this extra. So for cyclic task, instead of imposing an initial velocity and a final velocity, we will see, I mean, you can imagine that we can treat the initial and final knots as all the internal one. So we just impose continuity of velocity and continuity of acceleration, so that this initial equal final knots is treated like those intermediate knots. In fact, in a cyclic path, you don't recognize where you started and where you end. You're doing all these things. So the 2 extra conditions are not specifying a value for the velocity in 1 and velocity in n, not even saying that this value is the same, but just saying continuity of velocity and continuity acceleration. So 2 more conditions, and you square again the system. So this is just to show you that you can play around, and these 2 free parameters typically are used like this, but in case of cyclic tasks, there are other choices that may be convenient. Okay? So, having said this, I could simply conclude, saying, okay, you set up this 4n minus 1 equation in the 4 times n minus 1 unknown coefficient. It's a linear system of the form a times x equal b, and this is 4n minus 1 times 4n minus 1. These are the unknown coefficients of the n minus 1 cubic polynomials. And here and there, you put all the possible numbers that comes from imposing this coefficient and the data, so the value of the interpolating point and the initial and final velocity value. They could be 0 or not, so all data are there. But there's a more efficient way of doing this. And this is the algorithm that I will present next. So how do we build this? So this is, again, a representation of our problem for the generic joint. So Q1, Q2, Qk, Qk plus 1 up to Qn are the knots. And here I'm imposing some initial velocity because this is time I can talk about velocity, not just tangent or path derivative. So V1 is there and Vn is there. 0 or not, pay attention, could be anything. And now I'm specifying also the time instance, so T1, T2, Tk, Tk plus 1 up to Tn. So the total traveling time will be Tn minus T1. T1 is typically 0. So Tn is the total time. But it may be a spline that starts at some time and there is something before and there will be something later. So this is more generic. Okay. And then inside each of these you have a cubic polynomial, and we call these cubic polynomials with the letter theta. So theta k of time will be the cubic defined in the interval, in the kth interval, going from tk to tk plus 1, and this duration is denoted in this slide as h of k. Okay, so you will have h1 here, h2, hk up to hn minus 1 are the duration of the single subintervals. How do you write this generic cubic? Well, here we use this local normalization. So we restart each interval from 0. So we write that the generic kth cubic is index k, to remember that we are in the kth interval, and then this is the constant term, this is the first order term, second order and third order term in tau, and tau is a function that goes from 0 to hk. Okay, so we have not really normalized time, but we have rescaled their initial value. It's another way of writing things. It's not important how you write the cubic or how you write the polynomial, as I showed you on the blackboard. No? For the quintic polynomial, we could write it as just the power of tau, or in this Lagrange type form. So this is the one that we will use. What are the conditions that should be imposed to this? Well, it should interpolate the points. So it should go from when tau is equal to 0 in qk, when tau is equal to hk in qk plus 1. So the local. And this is purely local. And then here are the continuity at the internal knots. So pay attention how they are written. This is continuity in velocity. So I'm saying that this cubic function at the end, so when I evaluate it at tau equal h of k, its velocity should be equal to the velocity of the next cubic function, q plus 1, at the initial, at its own initial value, which is tau equals 0, because we have reset time. So pay attention to this. And similarly for the acceleration. And this for all internal knots. So n minus 2 condition twice. Okay? So I'm just rewriting things. So up to now, nothing has changed. When we set up all the conditions, it's in this form. But we make this observation. Suppose that, let me cancel this and rewrite it. So I have several points, not necessarily equally spaced, by the way. Then I have some initial value and then some final value. This is Tn and Qn. This is T1 and Q1 and V1 and Vn. And then I focus on a generic Tk plus 1, and this is Qk plus 1 and Qk. Okay, now I look at the generic cubic. And pay attention, if the problem was slightly different, the problem was go through these n knots, and at each knot I specify you also the velocity that you should have. So suppose that the velocity at the knots are specified. For instance, here I should start from here and go there. So this is Vk, and this is Vk plus 1. Okay, so for the moment, let's put it in parentheses. So this is not given, but suppose that they were given. So the problem would be completely decomposed. It's not relevant that this is the kth interval of many, because locally the cubic here is only defined by this boundary condition. Okay, so I will have something that will make like this. So knowing the velocity at the knots would solve the problem cubic by cubic. The 4 coefficients are specified by the 4 boundary conditions locally there. But pay attention, if you do this and you specify velocity like this, and then you specify, let's say, this is the following Qk plus 2, and you're specifying a velocity Vk plus 2, so you locally have another things like this, but here there's a problem. You don't know if you have continuity of acceleration. In general, you will not. Even if this velocity is the same for left and for the right, but there may be a jump in acceleration because there's no condition imposed on that. Okay? So these 2 arguments are used for setting up a very efficient algorithm, which says denote the unknown velocity at the knots, and not generic one, are exactly those velocities that will guarantee also continuity of acceleration. Okay? So denote them by Vk, Vk plus 1, and so on. If you had this in your hands, then you could solve for the 4 coefficients of the cubic in an explicit way, in closed form, as we said. So generic cubic at time 0, we should pass through Qk. So due to the structure, this is exactly the first coefficient. Ak0 is Q0, is Qk. Velocity at the initial point of the interval, so at tau equals 0, we should be Vk, which we don't have, but if we had it, then this should be equal to Ak1. And the other 2 conditions, so passing at time tau equal hk in Qk plus 1 and having a velocity at tau equal hk equal to Vk plus 1, this can be organized in a 2x2 linear system with the other 2 unknown, Ak2 and Ak3, so the 4 coefficients of the kth cubic, and this is the matrix of coefficient, which depends only on the duration of the interval, and these are the 2 unknown, and these are the data, brought everything on the right hand side. And then you can solve this 2x2 analytically. Okay? So if I had Vk, Vk plus 1, as mentioned, this would give, as for a generic point-to-point motion, all the coefficients. Now, what is left to be imposed? Of course, if we repeat this for all interval, the velocity, let's say, the right velocity of first interval and the left velocity of the following one will be the same. So we are using the same variable. So this is automatically satisfied, the continuity of velocity. What is not yet satisfied is the continuity of acceleration. So what I'm saying is exactly this. Here, I'm using this value both for this and for that. So the continuity in velocity is guaranteed. So here, I need to impose the continuity in acceleration. So I write down explicitly the acceleration of the kth cubic at its end, and this has this form. Okay? When I'm doing the evaluation for tau equal hk. So it involves these two coefficients, which have an expression given by the solution of the above equation. And then I equate this to the acceleration of the following cubic, evaluated at the initial point. And again, its expression is this. And this coefficient is the solution of a similar equation for the next interval. So this coefficient, and this coefficient are the only one that appears in this continuity equation, and each of them are a function of the local data, of the kth and the kth plus 1 interval. Now, if you organize this n minus 2 equation, because this is imposed for all internal knots, continuity of acceleration, you will end up with a system which is no longer 4 times n plus 1 times 4n plus 1 with some internal structure that I don't know, but these are only n minus 2 equation in the n minus 2 unknowns here. And the matrix of coefficients has a three-diagonal structure. And not only that, with diagonal dominance, which means that they can be inverted very easily with very little rounding errors, no matter how big is this matrix. This is the convenient part. Okay? So this is three-diagonal, always invertible, and always well-conditioned. And all the known data are brought on the right-hand side. So this includes the h, which are h1, h2, hn minus 1, so the duration of the n minus 1 interval, the q, q1, q2, qn, plus v1 and vn, which are known because these were given as to square the problem. Okay? And in particular, the expression of the coefficient matrix A for this reduced problem is only a function of the duration. Okay, and you see that it's dominant diagonal. So if you take any element on the diagonal, this is greater or equal, in this case equal, to the sum of the element in the same row, which are off diagonal. Okay, you can do also the thing by row, but you can see this by rows, in fact, not by columns. Okay, and the other thing is that since there are no q's or no v here, if I have to invert this matrix for the generic joint J in an interpolation of all the joints, well, the same matrix is the one for any joint. So I have to invert this matrix only one. Okay, because only the data on the right-hand side, those that goes into the vector B, will depend on the specific joints. And here are only the interval, and the interval are the same for all joints because we want to make a coordinated motion. We cannot go faster on joint 1 and go slower on joint 3. Okay? And similarly, just to look in the face of this, this is the B vector. Okay? And you see that only in the first and last elements, the V1 appears and the Vn appears, because they are really far away in this set of equations. So what are the properties of the spline? So first of all, this is we don't prove this. This is in textbook. If we are considering a spline for interpolating a sequence of knots, and we are not using time here, but space parameter, so now we remove all the timing information, we just working in geometry, then the spline is the function which, among all possible interpolating functions, minimize the total curvature of this path. So it's the smoothest interpolation function. And I'm not talking about polynomials. I'm talking about any function that interpolates the n knots. The spline is the one that minimizes this quantity. This is why we have some guarantee of not having wandering. I mean, if sometimes it goes up and down, but then it's in the data that you are requiring this type of overshooting. Okay. The other point, which is nice, is that there's a unique spline defined once you give, in our case, Q1, Qn, the interval duration, which may also be in space, not in time, and then the initial and final value of V1 and Vn, or the tangent, if we are working in space. So once you give this data, there's only one solution. And there's always a solution, okay? Now, the total transfer time is the sum of the interval, or the difference between the last time Tn and the initial time T1, okay? If T1 is 0, then, of course, the total time is Tn. Always the sum of the duration of the sub-intervals. So you can imagine that you can try to do a minimization in time of the motion. So you're trying to pass through this point, not having assigned the time interval, but trying to compress this, to bring them close to 0 so that you can do the motion very fast. But of course, in order to the problem to be significant, you have to impose constraints. And what are these constraints? Typically, maximum bounds on velocity and acceleration. The smaller time you take for doing point-to-point motion, the more speed you have, and probably the more the acceleration. So it's clear that you have a bound. The problem stated in this way is highly nonlinear. So you have to resort to a general optimization method. You cannot invert matrices. You have to really use a mathematical programming approach. There are functions in MATLAB that do the job, in the optimization toolbox of MATLAB. So this makes sense. And here is the condition that we commented. When you try to, when you have the case of a cyclic task, then it's clear that you have also the initial time will be, the final time will be the initial of the next cycle, okay? But this is not important because you're working with interval. Well, you may say, okay, I'm continuous, so Q1 is equal to Qn, I impose that V1 is equal to Vn. But again, in that point, you're not imposing continuity of acceleration. So the two extra conditions are obtained by imposing continuity of velocity and acceleration, but not a specific value of velocity at the initial and final point. Okay, so this is the difference. Now, last consideration that I want to make is what happens if in this framework we have also an additional condition on acceleration and on final acceleration. So we have two extra conditions beside initial and final velocity. Should we throw everything away, or how can we modify the approach? Do you have any suggestion or idea? So my point is now, suppose that we are exactly in this situation with V1 and Vn assigned, But suppose that here we have also, how to denote, an acceleration a1 and acceleration an. So 2 more conditions. We have already used up all coefficients, so what can we do? Well, if you think carefully, this is exactly what we have seen when n was equal to 4. With n equal to 4, we have start point, lift off, set down, end point. And there we were assigning v1 a1 and vn an, so the last value, and then continuity up to acceleration in the intermediate knots. So in that case, a 4-3-4 solution was okay. Okay? So generalizing things, I would say that if we use at the first interval and the last interval a 4th order polynomial rather than a 3rd order polynomial, we have the extra degrees of freedom to impose also this. But then the whole procedure should be worked out again. Okay? So it's not that you use the same formula that I showed you there. You should work out the formula. You can do this, but it's not immediate. So here I propose a different solution. The different solution is the following. Suppose that, okay, this is not A, is alpha 1 and alpha n, just to use the same notation as there. Now, the idea is, okay, you want to keep only cubic polynomial? Then take the first interval and split it in 2. And take the last interval and split it in 2. Okay? So you split first and last interval. So instead of using 1 cubic here and 1 cubic there, you're using 2 cubic here and 2 cubic there because you split the interval in 2. Okay? So, and what do? You split the interval, and then what you have to impose some condition. Now, in a fictitious knot, because there is no knot to pass through. So, since now you have n plus 1 cubics, remember, so you split, let's draw it here. So this is the first interval, T2, and this is whatever, the last interval. So I split this in 2, and I split this in 2. And then I have n plus 1 intervals, and so 4 n plus 1 coefficient. Because I have a cubic, each cubic is 4, so I've increased the number. And then I have the previous condition were 4n minus 1. Now I have to fill in, so this is 4n minus 4, this is 4n plus 4. So there are 8 missing conditions. And the missing conditions are 2 acceleration, alpha 1 and alpha n, and then continuity of position, velocity, and acceleration at extra knots. So here, you're not imposing a specific value because you don't have this value. You're just saying that the position from here is equal to the position from there, as well that velocity from here is equal to the velocity from there, and the acceleration is equal to that. So you have 3 continuity conditions here, and the same here. So you have 3 plus 3, 6, plus alpha and alpha. So these are 2 times 3, so the 8th condition that you were missing. So you re-squared the system, and now you have a solution where you have only cubic polynomials, 2 more than before, but you have done this splitting, and here you have imposed, like in all other knots, continuity of velocity and acceleration. The difference is that you're not imposing a passage because you don't have a knot there. You're just saying, you join the position. So position on the right is equal to the position on the left, whatever this value it is. You're not imposing this value. Okay? And then you remain inside the same thing. The only things that bugs us, which we can accept, is that depending on how you split this interval and this interval, for instance, at the midpoint or very close to the initial point, whatever you choose you make, you will get a different spline. Okay, so once you fix this, you have a spline. If you change, because there's no specification on how you split the first and last interval, if you change the splitting, you will get a slightly different spline. Okay? It's a minor problem, because then the algorithm works as it is. You can find the details of this in the textbook, this variation. Here I'm just using the results from there. So suppose now a simple case, otherwise it would take too long to describe. So suppose that we have n equal 4 knots. This is exactly the case of the 4-3-4 trajectory that we have designed in advance. But let's now handle it with only cubic polynomials. So 4 knots, 3 subintervals, so 3 cubic polynomials. If we specify initial and final velocity, that's it. Now we specify also initial and final acceleration. So the first and last interval, there are only 3, should be divided in 2, so that we get 5 intervals. Okay? The 5 intervals are from here to here, 2, 3, 4, 5. So the dots, the crosses are, or maybe not, sorry, forget. The initial interval are from here to here, then from here to here, and then from here to here. These are the 3 intervals. In fact, these are the interpolating knots. Now, here in this picture, there are shown 2 possible division of the first interval. So I take this interval and I divide it here, or I divide it here. And I take the last interval, and in this first case, I divided it here, so the 2 interval will be from here to there, and then this part, or I divide it here. Okay? And you see that when you solve the problem, you have different splines. This is the first interpolation one. They all passes through the knots. They all have same initial and final velocity and same initial and final desired acceleration. But the path is different, or the evolution is different, and same in velocity and same in acceleration. Okay, so this is the result. Just to show, in this case, the boundary velocity on velocity, the boundary condition on velocity were 0. In fact, you start from 0 and you end up in 0 in both solutions. Okay, and the acceleration were also 0, so you start and stop with 0 acceleration. Here you can see that these are cubics, these are quadratic function in each interval, and these are linear function in each interval. And you see when you're splitting with x's, so with the short initial and final interval, this is the first segment, second segment, third, fourth, fifth segment. Okay? So it's linear in acceleration and continuous, although the jerk would be discontinuous in this case. In fact, this would require higher order cubics, higher order splines, not cubic spline. Okay? So this covers quite the picture, and this is an example of the 2 different placement of the splitting of the first and last interval in order to recover the addition of acceleration boundary condition within the same previous formulation of cubic splines. Okay? So let's stop here before we start with the next